flip the screen around. Yeah. There. How does that look about right? Where we left off. So some of the themes. So we kind of just got done talking about scientific method, and then we were kind of looking at some of the major themes that we have in biology. I mean, obviously, some of these themes we're not going to really go into a lot of depth here because we've got entire chapters down the road to unpack all this. The cell theory is one of those. That is a big theme that we'll take a look at. So we have a cell chapter dedicated to that. Also, the molecular inheritance, right? So these are major themes. We've got cell theory, we've got the molecular component of inheritance associated with the transmission of genes from one generation to the next, right? So we have genetics to deal with that. And of course, we're going to look specifically at DNA a little bit. And so this is something that we have a little bit of exposure to in a couple of chapters, actually. So there's a lot that's going on in terms of DNA. A couple of things, just as sort of jargonish words that may require some decoding, is the concept of gene, right? So the gene basically is a sequence of DNA that controls a trait. Basically, that's what a gene is. So if you have dark hair, it's because you have the gene that encodes the information for dark hair, and that's so forth. Another one that I've kind of bantied around a little bit that maybe I didn't necessarily describe very clearly or specifically is the concept of a genome. And so the genome, there's a couple of different applications of genome that we have. So the genome specifically, I mean, I've been kind of sort of talking about this, but not really saying what it is exactly, right? So like the genomics and stuff like that, big jargonish words. So basically what all a genome is all the information that's encoded in your DNA, right? It's kind of like the master blueprint. So all that information that goes into making you is your own personal genome. So you've got your own genome. That is the complete set of instructions to make you from scratch. There is a human genome, that is to say all of our individual pots of information collected together to form all the information for the human species and all of our variation. That's the human genome. And so there's two different levels of speak of genome. A personal genome is just you and what you get from your family. And then the human genome is all of that, all 7 billion of us, all of our information in one big pot. Okay. So there's a couple of different ways you can look at it. So when you take a look at, when I said we sequence the human genome, we sequence the species level of the genome, not like one dude's genome, right? So it's like everything, the whole shooting match. And so we'll talk a little bit more about that. So that kind of wires into sort of this idea of heredity and inheritance and genetics and all that sort of stuff. And we'll get to that in chapter 12. The other big theme that we have in biology is also structure function, right? So structure and function is a big thing. This one will follow you actually all the way through AMP. So those of you heading toward AMP, this will follow you, kind of like a bad dream. It'll keep recurring. But the idea here is that typically in biology, because we have a particular set of questions we're trying to answer, right? Then that means we have a certain number of functions that we need to have in place in order to answer those questions, right? Well, here's the problem. In order to get the function that you need, you have to have something, a structure to give you that function, right? So here's a good example. I want you to come up with a structure to hammer a nail. So what are you going to come up with? A hammer. Okay, think outside the box. That's an easy one. Okay, hammer gun. That's still a hammer, but go ahead. Still the same thing. Keep going. A rock. That's significantly different than some sort of a hammer, right? So the hammer, hammer gun, air hammer, those are all variations of a hammer. Just a technological spruce up, if you will. But not insignificant, right? So hang on to that idea. It represents an approach that you have a lot of variations to that approach, right? So like if you were talking about an organism with all those roughly same way of approaching things, but slightly different, innovations to do it, those would represent multiple different species, right? So you'd have the classic old hammer species, then you would have the, hammer The driver, right? That's another one, and the air gun, that's another one. So that's would be 3 different versions of that same basic hammering idea. The rock would be a more distantly related version of that, because there you're just using something else, right? Or like, just use your enemy's skull or something like that, whatever, right? I mean, so it can get gruesome, obviously, but so I don't have Halloween to blame anymore. This is just the way I am. But anyway, because it's easy in fall, because I can say, it's Halloween. I just kind of get naturally dark in and around Halloween. I kind of pull out of it. But it's January going on February, so it's just me now. I have nowhere to hide on this one. So, right, but those are all variations of a function. So you have different structures that you've created to achieve the exact same function. Okay, and that's kind of a structure function sort of thing. Now, at the end of the day, do we care? No. If you drive the hammer, if you drive the nail in, success. Okay, but you have different structures in order to give you function. Matter of fact, if you actually take a look at the way we engineer a hammer, you can see that the way you engineer a hammer is very specific to what you're trying to do with it, right? I mean, you've got different materials associated with it. You've got a wood handle or a plastic handle. Why? For comfort and grip and leverage. There's a piece of function there that's very specific to that structure. And then, of course, at the end, you have something hard, right? Generally speaking, a good hammer is steel, the hardest thing you can find, right? And so that's because that piece has a very specific function, and you've designed a specific structure associated with it. A wood mallet, by the way, is it the same as a carpenter's hammer? No, because it has a different function, right? In this case, you're trying to like maybe hammer wood pegs, and a metal carpenter's hammer would absolutely obliterate those wooden pegs, right? So if you're a woodworker, you have that softer rubber wood mallet so that you don't destroy your wooden peg when you're trying to put something together. Okay, Evan, was that a question coming up? No. Okay, so I just I kind of saw a gentle rise of the hand, so I always make sure I cover it. Okay, so processing information, right? So information, this kind of goes into the DNA piece. This is important because in order to build structure, in order to do what we want to do, you have to have information to do it, right? Somebody had to have some sort of a plan, some sort of information to actually build the actual hammer structure itself. And so it all comes back to information. If you don't have a plan for it, then you're probably not going to build it, right? Just like every building that you see in Denver, a house, an apartment, a Walmart. I hate Walmart. The Target I used to like, but Target is now trying to catch up to Walmart in its destiny toward the toilet. At least the Target by our house. Both the Walmart and the Target by my house has an affectionate or not so affectionate name called the Dump. Dump number 1 and Dump number 2. It's where you go if you want to die.
Sounds like Target.
Yeah. Matter of fact, I mean, we travel miles out of the way to go to a decent store. So, and even then, it's like, wow, you're dysfunctional too. So, anyway, but that's my problem. And trust me, you will hear more about my problem with Walmart.
I don't know.
So I've got major issues with Walmart. I hate it and love it at the same time. It's very confusing, right? It can be. I mean, you can't beat the prices, especially if you got a family and you can't afford food. It's like a black hole. You don't want to go there because you know you're going to be destroyed, but it just keeps sucking you in and you can't escape its gravity. That's Walmart in a nutshell, right? But so basically what you have to have is you have to have information to do this, right? You have to have a plan. You have to have know-how to do that. And that's kind of what DNA does for you. It's an informational molecule. And it basically informs everything that you do. Ultimately, everything that you do. Literally, DNA will build you from nothing to where you are now. Every scrap of information is there. Okay, and that's kind of why it's important to sort of flow information, how you process information, how you utilize information, how you deploy information is a big strategy and a big deal in biology. Equilibrium is a concept that comes out of chemistry, right? Basically what equilibrium essentially means is that you basically have processes or chemical reactions or processes that are in balance with each other. And for the most part, they're kind of like in a state of non-change. So they're kind of happy where they are. If you perturb equilibrium, then that means you've changed the system. So you've kind of made waves for yourself, right? So think of like a calm, glassy pond. That's the state of equilibrium. There's not a lot of change there. Everybody's happy. And then you throw a rock in there. So you're disturbing equilibrium. And so you create these ripples of disturbance in the equilibrium. And then that creates some sort of an effect, right? So that achieves something. Generally speaking, when you disturb equilibrium, you're using that for your own purposes. Okay. For instance, if you were to stick an oar in the water, you're disturbing its equilibrium. Why? Because you want to pull yourself forward, right? Because otherwise you're just sort of drifting randomly. Okay. Generally speaking, in chemistry likes to think about equilibrium, but in biology, equilibrium is boring. And so biology tends to be dynamic. So what we want to do is we want to jack the system up, right? So we just want to start screwing up with equilibrium, because then we get really interesting and crazy effects out of it. Okay. That not just for fun, but they typically have biological benefit to them. Okay. So that's kind of the thing. So we are always going back and forth between equilibrium and a state of non-equilibrium. Okay, so bear with me because I did not queue up chapter 2 yet, but I will here in just a second. By the way, if you're wondering, I'm using the exact same PowerPoints that I posted for you guys. So you're seeing the same stuff that I'm using. There's nothing mysterious about it. Okay, so that's the end of chapter 1. Any questions on chapter 1? Okay, onward then. So that's all the intro stuff. Now we roll up the sleeves, both metaphorically and physically. So chapter 2 now begins with the beginnings, right? All of living organisms, we have our biological questions of life. We have some of our philosophical underpinnings with some organizational ideas. Now we have to actually go to the hard work of building a biological organism. So imagine that's the process we're going through. We're going to be building a biological organism. And so the question is, what do we need in place? Let's start building the foundation first. What is that foundation? That foundation is chemistry, right? So the foundation of all the universe is physics. They lay down the physical laws by which everybody, both living and non-living, have to play by. And then from living stuff, in addition to that, you have another layer of rules that you have to abide by, which are some of the rules laid down to us by chemistry. And then on that dual foundation of physics and chemistry, we can start building living organisms. Okay. So chemistry and physics creates the rules of the road for us. Okay. And that's the reason why we always start with chemistry. That's the reason. A lot of times students will be like, oh my gosh, are we ever going to get out of chemistry? Why are we like, is this a chemistry class or a biology class? It's like, well, every biology class begins as a chemistry class because everything is built on chemistry. Okay. So let's first of all go back to the beginning. Let's talk about matter, right? So matter basically has one basic definition. It's essentially anything that has mass, or alternatively, anything that occupies space. So if you take up space, then you are matter. And matter is basically made up of one thing. It's made up of atoms, right? So we kind of touched on that a little bit when we kind of went through our levels of organization, our hierarchy. The beginning, the bottom part is basically the atoms. Now, below the atom, obviously, is going to be subatomic particles and things like that. We'll talk about those here in just a second. But what I want to do is when we take a look at matter, there's really two major primary descriptors for it. We have obviously the atom, And we also have the concept of the element. Now, what is an element? And this actually gets described in our slides, I think a few slides down the road, but it's appropriate to deal with it here, just kind of as an introduction to matter, because it makes sense. At least to biology brain does. So what is an element? So an element basically, and I'm going to define atom here in just a second, but an element is basically any substance that cannot be reduced to any other substance. That's an element. It's pure. So here's a good example. This is a little gold ingot, something you'd find at, the mint or something like that, right? Pure gold, not gold plated, right? The real deal. So if I were to take a look at this, and I want to say, I want to kind of show you so it's pure. That means it can't be reduced to anything else, right? So, and I'm going to show you a couple, I want to illustrate that, but at the same time, as I do this illustration, it's also going to illustrate the concept of an atom. So let's define the atom first, and then we'll take a look at our little gold bar here, okay? So the atom can be defined as the basic unit of matter. So what does that mean? Just like the basic unit of the cell, right? We had to define what that meant. This also requires a definition. So this is basically the smallest unit, the smallest that we can get. I want to say unit. And still retain the properties of the element. Okay, so let's take a look at our chosen element. So what we want is gold. Anybody know what the elemental symbol for gold is? Yeah, it's AU. Right? Right there. Right underneath silver. And dangerously next to mercury. Although cooler than mercury. Okay. Of the element, correct. Yep. Okay, so now let's unpack what that means. So here's what I want to do. I want to take this pure gold bar. I'm going to cut it in half. This top section there, is that still gold? Sure it is. I'm going to cut it in half again. That top section there, is that still gold? No. Sure, we're good with that. I'm going to cut that one in half like that. Is that little corner piece still gold? Yeah. Good. I'm going to cut that one in half. Is that that rectangle still gold? Still good with that, right? So if we cut that little square right there, is that little square still gold? Yeah. If we take off a little smidge, that little smidge still gold? Yeah. Like a little blob. Yeah. Is that still gold? Yeah. Sure. If I break that down to a single atom, is that still gold? If it's one atom, is it still gold? Yeah. By our definition, the answer to that would be yes. Why? Because the atom is the smallest we can get and still retain the properties of the element. So what's the properties of gold? It's very conductive. Actually, the best conductor. Matter of fact, most of our electronics, if we really wanted to create the perfect electronics, we'd wire it with gold, not copper. As a matter of fact, I don't know if you guys have been down to the Space Museum down in Colorado Springs, but if you look carefully at some of their circuitry that they have on display there, you'll notice it's actually behind glass, obviously. But it's actually, they use gold in their circuitry because they need really, really efficient conductivity. What else? What's another property? You came up with the hard one, by the way. So the hard one's out of the way. What else? What? It is soft. It's very soft, right? So basically that kind of is linked to the, that's a manifestation or visible manifestation of the malleability of it, right? So it's easy to work with. It's distortable, very much so, right? To the point where one of the reasons why most of your jewelry is not pure gold, and any of you guys who have rings like or something like that that have a lot of high gold percentage, they're miserable, aren't they? because I mean, you start off, it's like, oh my gosh, it's a beautiful ring. And then like within a few years, it's just like a blob of Play-Doh, yellow Play-Doh on your finger. Yeah. Yeah, and it drives you crazy, right? Because you paid a king's ransom for that thing, right? So what heritage is that one that you have? Yeah, right. Because but if you have like intricate carvings on there or something like that, those things get smashed out, right? Because it's soft and malleable, right? This is one of the reasons why they have the lower carats. It's not because they want you to be able to afford it. That's a part of it as well. But like if you work with your hands a lot of times, like laborers, this is a big thing for them, right? Like they work with their hands all the time. They're always like outdoors or doing something very physical. A lot of times the jewelry they get is going to be low caratage. It's going to be like 10 carat. That's not going to be as yellow as you like it, but it's gonna stand up to the beating that your hands take when you're just working with your hands. Yeah, yeah, like if you kind of slam it down on a yeah, it's like it's crazy, right? And so that's a problem in jewelry, right? But that's only 18 karat, right? So if you go all the way up to full pure gold, it's even softer still. It's actually so soft that you can actually bite a hole into it. You can actually like take a piece of gold and like rip it off with your teeth. It's that soft. By the way, that's what they always used to do back in the day. So, the old trick of biting the coin, you've seen that one? You know why people bite coins? It's not because they like the taste of money. It's because back in the 19th century, we didn't have a uniform currency. Different states would have different currencies, and nobody had any kind of system to sort of homogenize. So like, for instance, a Nevada dollar would not be accepted in Colorado because we had different currency measures. It was like we were little different countries, and there was no way of exchanging it. So a miner who had gold or a gold coin, because they weighed gold, they kind of judged gold by weight, not by, oh, this is a $5 gold piece. They did it by weight. You give them a piece of gold and be like, is this real? Are you trying to pawn like some fool's gold off on me? So what would they do? Just do a quick check. They bite it. They could leave an indentation with their teeth in it, then it was real gold, you're good. If it didn't leave an indentation, then you're probably gonna get shot. That's just the way 19th century goes. So that's kind of, we kind of do the same thing now, don't we? We give somebody a $20 bill, what do? Right? That's the 21st century version of biting the coin. But the reason we bit it was because of the softness and malleability of gold. What's another property of it? It's actually not light. Like in terms of mass or density, it's actually quite dense.
Lower melting point?
That which goes along with and is related to, but not exactly related. It's a cousin, if you will, of the malleability, right? So there's another one. The most obvious one. I've already mentioned it once. What? Yeah. What color is it?
Yellow.
Yeah. Right. But it's a kind of a particular shade of yellow. Right.
Yellow.
Yeah, like it's got its own unique yellowness to it, but it has its own color name, right? So you call it gold because there's really not another metal that's kind of that shade of yellow. So it's got that's there's one more. I lied. I lie a lot, but there's one more. It's true for all metals. It's yellow, malleable, conductive, dense. It's quite heavy, actually. So melting point goes along with the malleability. Think of it, observe its physical appearance. Describe it. I'm blind. I've been blind from birth. I've never seen gold before, ever. Describe it to me physically. What does it look like?
Gold.
Shiny. Where is it? Somewhere over here, right? Shiny, luster, right? That shine is a property, a physical property of the element. So all those properties of the element are to be had at the level of the atom. The atom is the smallest we can get and still have all the information we need in order to encode those traits. Its luster, its color, its malleability, its conductivity, all of that. Now, what happens if we take the atom and we blow it up? Is it still gold?
Yeah.
No, right? Because now we are smaller than the level of the atom. And the atom is the smallest we can get and still retain those properties. Think about it this way. Instead of using a gold bar, I'm going to use you guys. You guys are 1111, yes? If I cut the room in half and I look at you guys, are you guys still 1111 students? Sure you are, right? If I cut you in half again, are you still 1111 students? Sure you are. If I come right in here and I cut you guys in half, are you guys still 1111 students?
On a good day, yeah.
Now, if I cut you guys in half, and I'm going to pick on you, it's because you're in the front.
Okay.
Yeah.
That adds up.
Are you still 1111 student?
Yeah.
Now, and you retain all the properties of an 1111 student. Now, if I tear off all your arms and your legs and your head, are you an 1111 student?
I'm still thinking, yes.
No, no, no.
Yeah.
Just head, left arm, right arm over there, right leg out the door, left leg in the back.
It's not.
Your torso's right here. Are you still an 1111 student? Do you still retain all the properties of an 1111 student?
No.
Correct. You're just body parts now.
Or just different parts.
Same thing with the atom. As soon as we blow you up, it's like tearing off all of your arm. So your most functional unit, the smallest that you can get and still retain the properties of an individual 1111 student, is you. As soon as I start now ripping everything off of you, you become body parts. You've lost your information to be a coherent and functional 1111 student, right? And so that's kind of what it's like with the atom. That's what we combine the two together. Because when we take a look at atom, we've already talked about those, right? So basically that's kind of our fundamental unit of matter. Everything is made up of atoms. And elements are made up of atoms, and elements are just basically pure samples of one particular type of atom, typically that we find in nature. Then the question is, well, that's nice. We talked about gold. That's always cool. We like that one. It's pretty. The question is, well, what other elements are there? I'm standing right next to them. So your periodic table, which is the governing document of chemistry, is essentially a table of all of the naturally, for the most part, at least the first 92 anyway, all the naturally occurring elements that we find in nature. Now, these guys down here, we've kind of greased the pig on these a little bit, right? So, I mean, some of these are coming out of the super collider. So these are, so these don't really actually live in real time and space. But like the main ones, like the first 90-ish or so something, I mean, these are elements that we find in nature in varying proportions. Some of them are more abundant than others, but we find them in nature. And this is what we have to work with. This represents, if you will, the artist's palette of colors that you have to work with to build the molecules that you need to build. Okay, especially the naturally occurring ones. Because our job here is to build a biological organism. So the question is, what are our materials? It's these. Okay. So now before we move on, let's go ahead and kind of start characterizing a little bit, since the atom is such an important structure in defining matter. Let's go ahead and kind of characterize a little bit what we actually have in the atom itself. So atoms have basically 3 primary subatomic particles, and we're not going to go into particle physics. So we're not going to get into gluons and bosons and quarks and all those sorts of things. I mean, that's interesting and fascinating, but that is a totally different field. In biology, we generally cherry pick our way through chemistry, selecting out the principles that we can apply to biology and letting the rest of them, letting the chemists fuss over all the rest of it. Okay. First of all, we have 3 primary dominant subatomic particles that we're going to keep a track of in biology. The first one is the proton. And typically the proton is a particle that is to be found, and there's 2 different regions in the atom. So the first region of the atom is the nucleus, so the dead center of the atom itself. And then the nucleus is surrounded by the electron cloud. And those are the two dominant regions of an atom particularly. So the question is, what's in each? Well, the first thing that we're going to see in the nucleus is the protons. The protons are pretty large particles. They have a pretty high mass. So they're pretty big. They're positively charged. And typically we tend to abbreviate a proton as P+. Okay. So let's go ahead and draw a nucleus here. I'm going to put in a couple of protons, and they are positively charged. So very big. Now there's another particle in the nucleus. That is the neutrons. The neutrons are neutral particles. That is to say they have no charge. These are also large particles. And they're usually abbreviated. I tried to like wipe it off like it's a whiteboard. N0 or N0. So these are neutrons. So yeah, you're fine. So the neutrons then we're going to add in there, and I'm just going to put a slash through them to say that they don't have any charge at all. Okay, like a 0 with a slash through it kind of thing. So those are your neutrons. And that's what's inside your nucleus. That's what forms a lot of the large particles of the nucleus. Now, around the nucleus is going to be a third particle, the electrons. The electrons are typically very negatively charged particles. These are in size vanishingly small. And they tend to be abbreviated E negative. So, and they're kind of whizzing around in the electron cloud around the nucleus itself. So here's the thing. This is by the way a term when I had Chem 101 a long time ago. Jim Symes, who's a really great guy, he used this term, vanishingly small. And I remember kind of thinking, it's like, okay, so is that just kind of like a a hyperbole? Is that just kind of like linguistic flourish to kind of make it sound a little more interesting? And because he was kind of a very sort of a practical kind of a guy, nice guy, really expressive. But he said, no, that was a hyperbole. That's actually the way I want you to think about it. He said, because of this, think of the word vanishingly small as an adverb, right? You're vanishingly small. What does that mean to you? Yeah, right. It's like vanishingly says you're so small. You're almost like right there on the cusp of literally just winking out of existence. You're so small. That's tiny. He said, that's the way I want you to think about electrons. And so these electrons, these tiny little things are out here whizzing around in the electron cloud. And they're just basically kind of whizzing around in this kind of cloud-like structure, just doing their little thing. Like a Bob Ross painting. Happy little electrons. Right? And maybe there's a little proton that lives right about there. It's all right. You got to look up Bob Ross. I'm serious. I mean, he's been dead for a while, but well, still though. I mean, he has been dead for a while, and he's like a total hippie. So, like, I don't think he ever got out of the '60s. I don't think ever actually. Bob Ross, yeah. Yes, it's like '60s. See Bob Ross, right? That's kind of the traditional, yeah. The kinder, loving type of version of that you think of at the '60s, not the angry, acid-driven, belligerent version of the '60s. '60s was a complex era, but that's basically what you have, right, in any given atom. So you have those three. And so it's kind of what it looks like. So here's kind of a couple of different versions of this particular atom. So we have two different atoms. So we have a hydrogen atom, and the hydrogen atom has basically one proton here and one electron. So you can see you got one little proton there. And then there's two different versions of it. So this right here is one representation of the atom. They kind of use kind of the electron cloud version of it. So what you see here in this yellow fog, this is kind of like this foggy area is basically like a statistical representation of where this electron that's whizzing around hydrogen can be located at any given time in space. Okay, Now, it doesn't necessarily mean that it inhabits this entire fog at the same time all the time. It means that this thing is moving around so fast, but it is bounded in this little statistical fog bank. Okay, so if I were to freeze frame it, it might be here one moment. If I were to set it back in motion, it might be over here the next moment. It might be out here the next moment, or it might be over here the next moment. So it's just whizzing around here, but it's basically bounded into the statistical fog. That's the cloud that we're talking about. Okay, it's kind of a statistical representation of where these electrons could be spatially at any given point in time. Okay, but they're constantly on the move. They're never just sitting there hanging out, just like, right? They're moving all the time. And so this is a slightly bigger atom. You can see it's an oxygen atom. You've got your 8 protons, 8 neutrons in this case. So you toss in a few neutrons and then you have 8 electrons. So you have 8 electrons out here whizzing around now. So you got all these guys just kind of whizzing around in this sort of yellow fog bank, this sort of statistical electron cloud out there. And at any given point, they'll be in a particular area, and they're going to be constantly on the move. This is the actual accurate way to think about electrons in an atom. It's kind of in this sort of statistical zone, this electron cloud where they can exist right now. A and B are the same atom. So in B, basically we have what's called the Bohr model. And this is a slightly different look at it, and a slightly more inaccurate look at it, to be quite honest with you. As a matter of fact, Dr. Dillman would probably be screaming right now because he is always a chemical purist. It's wrong. You probably come in here and say, like, you're teaching something wrong. It's like, in biology, we use this for a different reason than in chemistry. Chemistry, they're trying to figure out what do the actual electrons look like whizzing around there. Here, we're just trying to understand them better. And we're willing to sort of use the Bohr system to help us better understand what's going on with these electrons. Here's what this looks like. Niels Bohr, brilliant guy, Nobel Prize winner in chemistry. So really, really bright guy. Came up with this Bohr model. And actually, this was the first model. This one predates this one. So this kind of statistical fog bank came later after Bohr. The original idea was the Bohr model. We used to think about atoms as sort of like a galactic model, right? So at the center, you have the nucleus. In this case, you only have one proton in your nucleus. And then the electrons would orbit that nucleus in a definable orbit, very similar to the way we thought, to the way the planets orbited the sun. And so from that model, then you would predict that you should be able to, like you can with the planets, you should be able to calculate and predict the trajectory of these orbits, just like we can do in astronomy, right? We can calculate at any given point where any one of the planets are going to be in space. Why? Because they have a defined calculable orbit that we can predict, and we've got equations to calculate where they're going to be in, say, 6 months. We know exactly where they're going to be because we can calculate, because their orbit is very predictable that way. Yes. Well, it's not linear, but it was linear, but gravity kind of bends it in. So it's kind of related. It's kind of a corruption of linearity. But it does have that predictability from a linear system, right? So that's the way we used to think about it. And as it turns out, that's all wrong. It's actually nothing like that. Matter of fact, the electrons are just like a big chaotic cloud, just like zipping all over the place. It's like a crazy chaotic crowd of people just like running into each other, going in all different directions. And they're just like, it's just mess, right? That's the way it's really like. Now, the question is, what does the Bohr model do for us? Well, what the Bohr model does for us, and the reason why we teach it in biology is because the Bohr model is basically a diagrammatic representation of the personalities of electrons. So we use the Bohr model as a schematic to help us organize electrons and to understand how they differ in their personality, because not all electrons are the same. Okay. Now, this model up here is more accurate. This one up here predicts accurate spatial arrangements of electrons. So in biology, like in chemistry, they're always interested, okay, where is electron epsilon? You know, they'll give these guys little Greek letters and stuff like that, make it all sound cool and interesting. Right. So where's epsilon? Where is that one right now? Right. And then they want to know what that is. And so they would use this upper version to predict where spatially that's going to be located. Right. And so you can imagine there's going to be a lot of work in that one because you have to know both the velocity of the electron and the direction of the electron. So there's a lot of calculus that goes into that to try to predict something like that. In reality, the electron can break hard right, hard left, and you don't know where it's going to go. So they're wild, right? So it's tricky at best, but this is going after an actual discrete, accurate spatial presentation of the electrons. This one here is not spatially accurate. They're not arranged in nice, neat, tidy circles like this around the nucleus. But what this does is it helps us to organize the electrons according to temperament and according to personality. Okay. And that's what we use it for in biology, is purely as a diagrammatic tool to help us sort of differentiate one group of electrons from another. So we have a very different purpose when we're looking at it, which is the reason why we use the Bohr system. Okay, purely for organizational purposes. Okay, let's take a look at the atomic number. But before we do that, I'm going to drop a slide in here and I'm going to go off the charts where there be monsters. From time to time, I will do this. I used to do it a lot. I don't do it as much because I try to do it all on the slides for the most part. These blank slides sort of sketch out sessions typically are moments where I would do something like on the whiteboard. But since the whiteboard is not being recorded here, I do it on a blank slide. So that's basically our whiteboard moment. Okay. So let's take a look at this. So first of all, what I want to break down for you, because we're at that particular point, is I want to break down for you the information, chemical information around an elemental symbol. And there's a reason why I want to do this. Because oftentimes in chemistry, and even in biology, we oftentimes will just start writing stuff out. We put all these numbers all over the place, and we just kind of assume you're along for the ride. And a lot of times we don't actually stop to unpack it and sort of explain to you what these numbers mean. And why is it that we're putting the number here and not over here, right? So notationally. So what I try to do is sort of decode that a little bit so that you understand exactly what all the different regions of information are, what we mean by that. There's really, so this is like our generic elemental symbol. So imagine something like this, X, there's no X, right? But this is our generic elemental symbol. And there's 4 positions of information that we can put around any given elemental symbol. 1, 2, 3, and 4. So in position 1, this basically is our atomic number. Now, what is that? The atomic number is simply the number of protons in that particular element. This also, the number of protons, serves as our atomic ID. So it defines who you are. And so to sort of underscore that, I always like to kind of use an example. Of carbon. Typically speaking, the atomic number on the periodic table is always given usually at the top. It can be dead center in the top, centered. Sometimes it's shifted to the right, usually not shifted to the left corner, although every now and then you do see some periodic tables arranged that way, but it's somewhere at the top. Okay. So if I were to take a look at carbon on the periodic table, what would you say the atomic number of carbon would be? Yeah, it's 6. So that's my atomic ID. By the way, just to kind of fill this one out, this is a fairly simple one. Underneath your elements is typically mass. Okay. We'll talk a little bit about that a little bit later on. But 6 protons is what carbon has, right? So that's the number of protons that it has. It's also its chemical identity. So if you have 6 protons, guess what? You don't need to tell me who you are. I know who you are. You're carbon, right? So here's how the ID works, just like an ID number for us, right? So if you've got like, let's say use your S number. If you change your S number by 1 digit, does CCD recognize you anymore? No, it's like you become another person, right? Same thing is also true here. If I add 1 proton to my carbon, am I carbon? What have I become? Yeah, because now I've got 7 protons, and that is the identity for nitrogen. If I were to take a proton away, am I still carbon? No, what have I become? Boron, right? Which has an identity, a proton number of 5. So an atom cannot change its atomic number without changing its identity. And generally speaking, most atoms, as long as they're happy, and we'll talk a little about what happiness means for an atom, as long as you're happy, you generally prefer to be who you are. So if you're carbon, you generally do not want to become something else, right? You want to be who you are. So for you and for most atoms, the idea of changing your identity into something else, adding or subtracting protons, is off the table. The only time we see that is under extreme levels of stress, when atoms are so unhappy and so unstable that they're willing to become something else in order to become more stable. That's true for radioactive atoms, which tend to be so big and unstable that they're willing to become something else in order to achieve stability. Okay. So that's number 1. Number 2 is basically where we write information for our atomic mass. And the atomic mass is the number of protons plus the number of neutrons. Why not electrons? Yeah, they're vanishingly small, right? So it's kind of like weighing a watermelon. If I ask you, what's the weight of that watermelon? Do you account for the dust that's on it? No, because it's negligible, right? It doesn't add anything to the weight. The weight of the watermelon is the watermelon, all the water inside of it. Just like the weight of an atom is overwhelmingly the weight of the protons and the neutrons. Those are large particles. They form the majority of the mass. So much so that we don't even consider the electrons. Even when you have lots of electrons, like these guys down here, these metals, okay, you still don't have enough to matter. Don't know what I did there, but that mean? Blue light filter? No. I like the idea of blue light filter, but I don't want to play with that right now. Okay, I don't know what I did. So you guys can't see it, but I can, and it's driving me nuts. Okay. Sorry. Like all sorts of little messages coming at me, so it kind of makes me a little nervous. It's like, what? Something blowing up inside there? Anyway. So that's your atomic mass. You tend to write it up in position number 2. So here's a good example. Let's take a look at carbon. So carbon has a mass of 12. All right, so you'd write that in position 2. So that'd be carbon 12. That's normal carbon 12. However, there are other carbons. There is a carbon 13, and then there's also a carbon 14. Right, so alternative masses, but same stuff, right? So here's my question to you. Carbon 13, carbon 14, and carbon 12, what's causing the difference in mass? So not the protons and neutrons, but specifically The neutrons. Why? Why not the protons?
Because the protons can't change because it will change.
Because it won't be carbon anymore, right? So because it's all carbon, 12, 13, and 14, you know that the protons have to be the same, all 6. So the only thing you have to change is the neutrons, right? So that's basically atomic mass. So you'll see atomic mass, usually if you're working with nuclear chemistry, things like that, like uranium-235, uranium-238, things like that. Those are different. Those are mass numbers that we are writing. So for instance, another way to write this out is to write it out like carbon 14. So that 14 is a mass number. Okay, position number 3. Position number 3 is the charge on an ion. This is basically when the number of protons is not equal to the number of electrons. Generally speaking, all of the naturally occurring isotopes, all the guys that are represented on this document right here, are all neutral. So that's the reason why I can confidently say it's like, oh, well, look, magnesium has how many protons? 12, right? How many electrons does it have? Has 12, right? Because unless otherwise told, we're looking at natural magnesium as presented on the periodic table, which is neutral. That is to say, for every positive you have, that is every positive proton you have an equal number of negatives, electrons, to cancel it out, to maintain neutrality. Now, what happens if those are not equal? Then you've got yourself an ion, okay? So generally speaking, your ions will come in a couple of types. So you usually will have either a charge of -3, -2, -1, a 0 charge, which will be neutral, will have nothing written by it, or you will have +1, +2, or +3. So over here, basically the number of protons is less than the number of electrons. And over here, the number of protons is greater than the number of electrons. So to create a positive ion, how do I do that? What happens to the atom in order to create a positive ion? How does it get a positive charge? It decreases electrons, right? Does anybody want to favor adding a proton? You guys are like, you're smiling at me, right? Because you're like, you're trying to get us, aren't you? No, but the reason is because that's a common mistake when you're first starting out, because you see the positive and you naturally think additively in your brain. That's just the way your brain is wired. And you think, oh, in order to get a positive, I need to add more positive, right? That makes sense. But the problem is, if you add a positive proton, what have you done to yourself? You've created something different, right? So you become something different. You change your identity. So assuming that you don't want to change your identity, can you add a proton ever? Do you change the number of protons here? So the only way you can create an ion is by what? Removing electrons or adding electrons, right? If you remove or lose electrons, you become a positive ion, right? If you add electrons, you become a negative ion, right? Because you've got extra negative charge that your positive can't cancel out, and that makes you negative. Or you lose electrons, you have extra positive charge that's not getting canceled out by the electrons, and you become a positive ion. Does that make sense? We'll write that up here in the third. So for instance, sodium oftentimes will form a +1 ion. So we oftentimes write it like that. Chloride, for instance, on the other side, in group 7, will actually form a negative ion. That's kind of the way they exist. Sulfate will form a 2 negative ion. It's a polyatomic ion, but it'll form a 2 negative ion. For magnesium, right, we just looked at that one. That's a -2 ion, okay? So you can see that whenever we're writing numbers up there in that upper position, that position 3, we're telling you the charge on the ion that it makes. Now the last position is position 4. Now what's going on here? This basically is telling us the number of atoms in a molecule. So here's an example. C6H12O6. Anybody know what that is? we'll see that again. We'll talk about that a little bit in a few chapters. Yeah, glucose is the most common answer. There's a few other things that it could be, but this is a molecule of glucose. So this is one total molecule of glucose. So in this particular case, how many atoms of carbon are in one molecule of glucose? Yeah, how many atoms of hydrogen are in one molecule of glucose? 12, right? And how many atoms of oxygen? So it's telling you in position 4 how many atoms of that particular the element are in that particular molecule. Okay. And so when you're kind of going through and you're just making these notations, you just kind of riff through it all, you start roaring away. And a lot of times it's like, oh yeah, by the way, if I'm writing something up here, this is what I mean by it, right? So they just kind of start writing. And so now that you have notational information, you kind of know that what's basically happening when we write stuff in those positions. Okay. So let's go ahead and head back to our list here. So there's that. Good. That should be recorded because I'm still screen sharing and it's capturing everything on my screen.
Okay.
So what you're seeing here is what I'm actually projecting as if I was a student who's logged into Zoom, seeing Zoom. So this is what should be recorded.
Right.
So what you're
Along with your voice.
correct. I mean, unless I did something stupid like hit the mute button or something like that, then in which case you just see a bunch of writing and you don't hear anything. That does happen from time to time. But the good thing about having 3 of you sections is that between the 3 of you, I've got to get it right at least once, right? So if I do something like that and it's like, you know that recording that you did, you have the mute button on, we can't hear anything on there, or you forgot to screen share, right? That's another one. So we can't see anything, we can hear you, but we can't see anything. So when that happens, and it probably will happen, then usually I'll just pull a recording from one of the other sections and post it for you guys. Because the chances of me making the same mistake 3 times basically means I need to check myself in to memory care. Yeah, yeah, that would be a really bad day. But the nice thing is I can't screw that up too badly, right? Because I don't have all 3 of you on the same day. I've got 2 of you on the same day, but then I've got the Tuesday, Thursday. So I can't possibly get everything wrong, like multiple days in a row.
That would be a really bad week.
That would be a very bad week. But I even have like previous semesters recording. So even if I really get desperate, I could pull some of those out and still kind of scotch tape it together. So I may not be the most gifted person in the world, but I am resourceful. So
We all tend to be.
Yeah.
Hope to.
yeah. Okay, so atomic mass, right? So this is basically the sum of protons plus neutrons. And oftentimes when you're going for mass, a lot of times people are like, well, what is your mass, right? And this is actually a big deal actually in chemistry, because normally we usually think of mass as like grams and stuff like that. But how do you determine mass of something that's atomic and you can't actually put that on a scale? It's too small to figure out what that is. And so there was a lot of difficulty in trying to figure out what exactly the mass of a proton was. I mean, we didn't know how to do that. And so a lot of times we have kind of protons and neutrons as sort of like a standard, like a reference point. And we have crazy units named after people like the Dalton, right? Right. So like a proton and neutron roughly has the mass of a Dalton. And a Dalton is a unit of mass measure. We generally don't use it a lot in chemistry. We usually use grams per mole in chemistry usually. But a Dalton is something we usually use in like protein work. So like if you get into biochemistry and you work with proteins a lot, then your masses are all Daltons, right? So a lot of times proteins are actually named after their mass. Like there's a protein that we'll run into in chapter 10 called P53. The 53 basically means it's a protein of 53 kilodaltons, right? That's basically what it means. There's another mass unit called an atomic mass unit, 1 AMU, and that's kind of a referential point. So it's kind of thing we said, well, let's take a proton and a neutron because they're roughly the same. And let's just call that 1 AMU, so 1 atomic mass unit. So that'll be our reference point. And then everything else will be fractions of that central unit. Okay, so you'll either be roughly bigger than a proton or smaller than a proton. So that's one a kind of a common one you see a lot as well. Now we can actually discretely measure the proton, the electron in grams because of the technology we have with super colliders and stuff like that. So, but we didn't have that back when we were first building all this stuff up. So that's all well and good. Protons and neutrons are all interesting, certainly, but electrons are really, really, really what we want to focus in on in biology, because electrons are essentially the particle of the three particles that gives us what we want, which is essentially the ability to build molecules, and then to build organelles, and then to build cells, right? That's the process we're at. So we're going toward from atomic to molecule. That's the levels we're going at. So when we take a look at electrons and we take a look at the idea of the ions, right? So we already talked a little bit about positive ions basically having more protons than electrons. And typically when you have a positive ion, you have a specific term it's called. So it's called a cation, which you hear from time to time in chemistry. You don't hear that hardly ever in biology. We just talk about ions, right? So it's understood that there's a few, like maybe a half dozen ions that we talk about that are positive in general, and you know what they are, right? So we don't have to tell you that sodium is a positive ion, because we work with sodium so much in biology that we already know that it's a positive ion, right? You don't have to tell me it's, oh, that's an Na plus. It's like, of course. I mean, it's like we're so familiar with it. We already know that. I mean, we've got like a sodium ion tattoo on us somewhere, right? So we know it. Now, in a negative ion, you basically have fewer protons than electrons. Why? Because you have added electrons, right? But then that we would call it an anion. Okay, so that's basically what we do. And then we'd have a net negative charge. Now, that's all well and good. So that explains kind of the ion situation. But then let's get to this other idea, the isotopes idea. So now, what exactly is an isotope? Well, an isotope is basically, like what we said, is basically an atom or a group of atoms that differ only by the number of neutrons. So for instance, when we looked at carbon 12, 13, and 14, those are isotopes. Isotopes are all the same, carbon, but they vary from each other based on the number of neutrons they have. Now, why is that important? Well, it's important because typically with these isotopes, they will basically form radioactivity. Now, not all isotopes are super radioactive, but radioactive elements in nature are isotopes typically. So you have radioactive isotopes, and these isotopes tend to be unstable. Remember, the idea of radioactivity and instability of the nucleus go hand in hand. You don't want to be radioactive, generally speaking, unless you are powerfully unstable. How do you get unstable? Simple. Too big. Generally speaking, too many particles in the nucleus. Think about it this way. A nucleus is kind of like a lot like you after a shopping trip, grocery shopping. Only since we don't have bags anymore and you don't want to pay for them, you've got a trunk full of stuff and you're trying to figure out how to transport it because you don't have bags, and you're swearing a little bit, and you're swearing at Walmart because that's where you were. Although actually probably Walmart doesn't care. They'll be like, whatever, take whatever bag you want. They could care less. But you're still swearing, right? But here's the thing. There's only so many things you can carry, right? You pick up a few things. Are you comfortable? Pick up a few more. You didn't let the other ones go. You added more to it. Are you still comfortable? Kind of have a little bit of an arm load. You're like, okay, I can do this. You still okay? You're not desperate, are you? Now, what if I take that much that you have out of the trunk and say, like, here, put all that on you now. And so you kind of got all this stuff in your arms, right? You've got one milk jug on one pinky, the other one on another pinky. You got the ring fingers involved. You're trying to figure out how strong those minor fingers actually are, right? You've got a couple of things in your teeth, and you got a whole bunch of stuff in your arms. And if you're clever, you might kind of like be doing this sort of thing, the whole tabletop walk. Right? Okay, how stable are you now? guess what? I'm not done with you. I'm gonna add some more stuff on. I'm gonna add even a bigger pile up there. It's kind of jiggling a little bit at the top. Imagine it's going up to the ceiling there. And so here you are. Right? How stable are you? Are you happy right now? Are you swearing? A lot.
Probably not, because you have something about.
Well, you're swearing in here, right? And you right? And of course, I put the eggs on the top.
Are you have them getting crushed?
Yeah, right. Are you happy now? Yeah, right. You and the bread's up there somewhere too, right? So, right. So, but yeah. So, what do you want to do now?
Oh.
Yeah, you want to shed mass, don't you? Why? Because you are powerfully unstable. You've got too much in your arms, and you're not going to make it. Normally, do you want to drop stuff? No. But when you're like this, and all of a sudden you hit an icy patch, and you can feel your back going, what are you going to do then? Everything is like, okay, screw you. I'm out. I'm not going to go to the hospital because of you. Okay, thank you, Walmart, son of a, right? Son of a Walmart, right? Son of a Cronky, or Rob Walton now that pretty much Walmart owns all of Denver sports.
Yeah.
That's hysterical. That's I don't know. I don't
They
think
pretty
any.
much own a town.
Well, in Arkansas.
Yeah.
Yeah, basically. But they also pretty much own Denver. I mean, you own all the sports teams, all the big ones. You pretty well own us. So that's just welcome to Walmart. So we say, welcome to Denver. No, welcome to Walmart. Enjoy your stay. You'll never leave. You'll die here because it's a black hole. But anyway, it's just bizarre. I've never actually seen a city like that. That's just all the sports teams, all the big ones are all owned by like one family. I don't think there's anything quite like it. Even in New York, it never got like that. It was close, but not like that. It's bizarre. But anyway, unusual. We'll see if it works out for the Broncos. I don't know. So the idea is because you're big, you're unstable, right? Just like you with your armload of groceries, you've got to figure something out, right? You have to shed mass. Why? Because you'd rather not, right? But in order for you to become more stable, you have to get rid of something. And so that's kind of what you start doing when you become radioactive. You're so unstable because you're so big, you have to start shedding mass somehow. And when you do that, that's radioactivity because you shed mass and at the same time you shed energy with that mass, and that energy is radioactivity. Okay. And that's what all radioactive isotopes do. Now, here's the cool thing. Radioactivity, when we actually measure, like if we were to take something that's radioactive and we were to, we can measure the emission of the radiation coming off at us. Typically, radioactive emission has what's referred to as a half-life to it. And basically what a half-life is basically the amount of time it takes for half the sample to radioactively decay. That is to emit, okay? And so generally speaking, when you look at half-life, so this is your time, this is the amount. So generally speaking, the time at which you have half of your amount is your half-life, which we usually will write as T1/2. But remember, only half of your sample is gone. You still have that again to go. Okay. And the amount of time it takes to get down to this point varies depending on the isotope itself. Different isotopes will have different half-lives. And depending on what that is, you could be stuck with radioactive decay for a while. So how do we put that concept to work for us? Well, there's a couple of applications we have. And I want to kind of get to that concept of half-life. But the first thing I want to kind of do is sort of illustrate that sort of shedding piece with a couple of applications, right? And I want to use carbon dating. How many of you guys have heard of carbon dating? So carbon dating is a common technique that we use to date the age, if you will, of a carbon-containing source, okay? And it's based on the isotopic nature of carbon. So we already established that carbon comes in a 12, a 13, and a 14 variety, right? There's a couple of things I want to highlight first of all before I circle myself back around to half-life. So these are 3 isotopes of carbon. These are naturally occurring isotopes. So in any carbon source that you have out there in nature, you will have all 3 of these. How many of you guys have eaten something today? You ate carbon. You actually ate all 3 of these. You ate all 3 of these in their naturally occurring abundance. How do you know these are naturally occurring? This is why. I want to point something out to you. Carbon-12 has how many protons? Yeah, not a trick question. It's got 6. How many neutrons does it have? Okay, good, 6. According to our calculation for atomic mass, what is the atomic mass of carbon? Not a trick question. 12, right? What is the actual mass of carbon? Yeah, the actual mass is 12.011. Do you see a problem with that? For you, does 6.000 plus 6.000 equal 12.011? Do you see the problem with that? Does one whole number plus another whole number ever give you a non-whole number? But isn't that what 0.011 is? Even 6 electrons is not enough for 0.011. You're a 1/10 of a proton at that point. Does that bother you? Do you have a question there? It's like, well, I'm making you think about it now, right? Your brains are hurting. It's like, think about it. Take a look at all the elements on the periodic table, all of them. Do you see any of them that are whole number ratios? Helium, that's the only one. Oxygen. Nitrogen's close. But most of them are fractions. Think about this for a second. Is it possible to get 0.81 of a proton? No. Doesn't make any sense, right? That's like saying a family is about 2.5 kids. It's like, okay, which kid did you cut in half? Right? It's a little gruesome. Does that bother you? The universe doesn't add up. So where does that 0.001 come from? Or where does that 0.92 come from for arsenic? Or for gold, where does that 0.97 come from? Or the 0.59 come from for mercury? Where does that come from? It comes from these guys. Because when you weigh a certain amount of an element, it's not just carbon-12. It's carbon-12 with a less abundant sample of carbon-13 with a less abundant sample of carbon-14. So the overwhelming majority of your carbon source, if you broke it down, is going to be carbon-12. But there's going to be a small percentage of carbon-13 in there, which is heavier, and a small percentage of carbon-14 in there, which is going to be heavier. So in a way, the heavier isotopes is kind of like you putting your thumb on the scale, just a little bit. And how heavy those are will depend on what that ratio is. For instance, if you take a look at which arsenic, right, 0.92 or gold 0.97, the isotopes of gold are heavier because they're closer to 1. So you're putting a little more pressure on that one. The weight of the heavy isotopes of carbon or nitrogen is a little lighter because you're not even getting up to 0.1. So that's a little bit of a lighter touch, but it's there. It's enough to create a fraction. So what you see in this actual mass is the overall average of all the isotopes factored in nature, not just the dominant isotope, because otherwise they would all be whole numbers, right? So that's coming from these less abundant heavy isotopes. That's where that's coming from. So these guys, generally speaking, the heavier isotopes are fairly unhappy. Everybody wants to be this one. Now, generally speaking, carbon-13 is unhappy, but it's kind of somewhere in the middle. It's okay. For the most part, if you're carbon-13, you're probably pretty stable. You're stable enough. You're not really interested in going anywhere. It seems like a lot of work to be radioactive, so I'm just gonna be like, I'm okay with this, you know. It's not ideal, but I'm gonna stick with it. Yeah, well, not quite. So helium, these guys over here are going to be, there's this very specific, we'll see these guys here in a second, in a little further down the chapter. So we'll talk about those guys. But the thing is here, you've got too much, right? So you got too many in your hands here. So the thing is you want to emit mass. So what are you going to get rid of? Yeah, why not protons? Yeah, it'll change the element, right? You would rather not be something else. But remember, this is the case when you will become something else if it means you're stable. So here's actually what happens. So carbon-14 will actually kick out a neutron. And that neutron will actually convert into a proton. How? That's a physics thing. I don't know. That's not my thing. Somehow it kind of converts it into a proton. I'm not quite sure how exactly. That's a particle physics thing. It does sound complicated. It's probably got a very interesting answer. I just haven't gotten that deep into particle physics to matter, mostly because in biology, we sort of like, oh, isn't that cool? Let's go ahead and do the electrons, right? So that's kind of where we go. But what happens if this guy converts into a proton? Well, what happens? So it stays here, right? So what happens to this? Is it carbon anymore?
Yeah.
If this turns into a proton? Yeah.
Oh, no.
What does it become? It becomes a nitrogen, right? Because now it goes from 6 protons to 7 protons. But guess what your mass is? What's your mass? Well, no, your mass. 14. What's the mass of nitrogen?
No.
Kind of nifty, isn't it? All you have to do, yeah, granted, you're going to become nitrogen, but you will become a pretty stable nitrogen. So really what happens is carbon-14 converts itself into nitrogen, becomes more stable. Your mass is already there. You didn't get rid of your mass per se. You converted your neutron to a proton through some sort of a clever particle physics process. And you basically converted yourself into a very relatively normal looking nitrogen with a mass of 14 and 7 protons. Not too bad. And all that, but guess what? Now that you call yourself nitrogen, you feel much, much more stable. Because now that you've allowed yourself to sort of crawl out of the uncomfortable skin of being an oversized carbon, you now be like, hey, you know, you're nitrogen now, but you're like the perfect size for nitrogen. Right now, all of a sudden it's like, hey, it just all fits together, right? So that's decay. Now, what happens when that process happens? So when you do that, you emit energy in the form of radioactivity. And not only that, but here's the cool thing about radiocarbon dating, is in carbon dating, because all carbon sources that you consume have the same ratio of carbon to them, we can actually measure the ratio of carbon-12 to carbon-14 in you. It should be the same as the stuff you eat. So the food you eat should have the same ratio of 12 to 14 as you have in your own body cells. And as long, because your carbon-14 is constantly decaying, right? So your carbon-14 supplies are diminishing over time, very slowly, but they are diminishing over time. So in order to keep those ratios the same, you keep replenishing that source of carbon-14 by consuming new carbon in the form of eating things that already have replenished sources of carbon-14 in them. So as long as you keep replacing that carbon, you're continuing to maintain those carbon-14 ratios identical to nature. The second you die, you're no longer replenishing those sources. Your carbon-14 decays and those ratios start to change. So since they change in a physics fashion, we can actually take a look at your carbon ratios now as an ice mummy relative to the ratios that we have in nature that are current. The difference between the two can be extrapolated back in time. So over a certain number of years, you will have gotten to this ratio. So we can extrapolate back and say, well, you've lost enough carbon-14 to be about equivalent to you being alive for the last time on this planet about 3,000 years ago. And that's how we do carbon dating. But there's a catch. There's always a catch. All right. Isotopic dating is one of those really cool mechanisms that we have in dating. But isotopes will have different half-lives. There's our half-life thing. So for carbon, I think it's like 5,700-ish or so. That means in 5,700 years, your carbon sample will have diminished by 50% or decayed by 50%. Generally speaking, carbon dating is only good for at most, I mean, this is really stressing it out, probably 20 to 30,000 years. We generally don't use it that far out because the further out we get into here, the more inaccurate it gets. Because here's the thing, and this is always an assumption. And there's some of this dating, this kind of gets into like, you know, we're trying to figure out like the age of a rock or something like that. How many billions of years ago was it formed initially, or hundreds of millions or whatever. The isotopic dating, which is very powerful, has one very, very tricky assumption that we always have to be mindful of. And that is that the ratios we see today are exactly the same as the ratios that have been in whatever the past is. Now, for carbon, that past is maybe tens of thousands of years. Not necessarily a bad assumption, but when you have an isotope, like for a rock, and you're talking about, okay, so I'm saying the ratios here are the same today, because that's what we're measuring, that's a reference point. And like 300 million years ago, they were the same. Well, they might have been, but you're kind of assuming that you know what happened in those 300 million years. Or not, right? Because there are things that can happen that can change the ratios. And the thing is, unless you're absolutely certain that nothing like that happened, then you always have to factor in the potential that, well, it's maybe 300 million years old, but we don't know if something weird happened back there that might have screwed up those ratios. Here's a good example for carbon. For carbon, the idea is the ratios are the same as in the distant past, as long as there wasn't any kind of influence of additional carbon between now and the time the person died. What are those influences? Fire. So if you have a person who went through a fire, they will have an abnormal ratio. So that will screw up those ratios and make the individual look completely off whack. So your dating will be off scale. And this is always one of the big problems, especially like carbon dating, because we'll look back and like the Shroud of Turin, that was a good one, right? They would try to carbon date that one. But the problem is the Shroud of Turin went through a fire. And so that's a problem. They can't get an accurate date on that because of the excess carbon that was introduced during the fire skews those results. And the same thing's true to a lesser degree for like isotopic rock dating and things like that. And there it's just more of like, well, we had a lot of volcanism. I mean, there's a lot of catastrophe going on there. I mean, the rocks are melting into magma. The gases that we use for isotopic dating are volatile, so they're evaporating out of the rock. That's changing it. So we don't know if there's any other episodes like that between their original creation and now that could change those ratios. We're assuming there wasn't, but we don't know for sure because we weren't there to document that, and we'd have to like dig into it. So it's an assumption, and a lot of times it's accurate, but there's sometimes where it's like, I'm not sure. So there's a huge range, right? So we just say this could be anywhere between 100 million and like 500 million years old. Like, why the range? It's like, well, because we're not sure if there's some weird thing that happened and it screwed those rates up, those ratios up. So that's just basically that's just part of the parcel to radioactive decay. That's just kind of the way it works. Different things will happen, but assuming nothing happened, they're really good. In terms of half-life, not every isotope has the same half-life. Like carbon has 5,700, plutonium, right? The bomb maker's choice, or the Fukushima choice, right? So your nuclear power plant choice, has a half-life of 26,000 years. As a matter of fact, that's really the real big reason. Have you ever wondered why we don't have like a nuclear society? Like, why haven't we envisioned or realized the vision of the 50s, right? Which is to have like nuclear toasters and like nuclear watches and nuclear toilets. And I mean, it had all sorts of nuclear appliances going on, right? Why can't we do that? It's not because we're afraid of blowing ourselves up. That's not it. It's really the death pill, right? The suicidal pill of nuclear industry. And the reason why we can't expand that as an energy source is because we don't know what to do with the waste. Because when the fuel rods are spent, they are still radioactive and we have nowhere to put them. So what do? We bury them in a mountain in Nevada, right? I mean, we store our nuclear waste there. We drop bombs on it. We keep our aliens there. I mean,
It's just hot.
yeah, Nevada is just like, we just do all bad things to
All the
Nevada.
senators go there.
Yeah, right. Yeah, right. So all the Las Vegas, right? So everything that happens in Vegas, it's like the anti-Vatican, right? So it's like you go to Las Vegas to screw up eternity, and then you go to the Vatican to get it back, right? So it's like, yeah. So right. I mean, so that's what we have, but you can't do that forever, can you? That's not a sustainable strategy. You're going to have a really big trash problem and a dangerous trash problem in a very short order. That's the big reason, because you're living with that nuclear waste for 26,000 years. Oh, no, wait. It's only half done by that. It's another 26,000 or more before it actually gets down to levels where it's going to be safe again. So think about that for a second. We haven't even had 26,000 years of recorded history. So what that would require is a very sound and disciplined waste strategy and a maintenance strategy for our nuclear waste that doesn't just cross generations, but crosses tens of thousands of generations of human history. And one of the things, unfortunately, I'm not a humanist. I do not think that the human species is great at all. We're a bit on the thuggish side, but we have not done anything right in human history to even get close to approaching that level of cooperation across that long of a time period. We have flashes of it, like we'll get really good for like a few years, and then we'll go off and slaughter half of ourselves, right? That's kind of the way we do it. So we just prove to the world that we are not as great as we think, over and over again. Just refer back to the Nazis for one of the more horrible chapters of all of that.
Yeah.
That's basically human history, actually, most of what human history's been. So the Nazis actually weren't really all that new. It does get that ugly, actually, on a fairly routine basis. We've actually been trying to do good. That's fairly recent. And we're not very good at it. That's kind of what we've proven there. We're really bad at that. Yeah. So it's like on our best day, we're still like killing each other. It's like, it's like we give each other a hug, and it's like we just kind of like suffocate each other. It's like, here, good, die, right? It's like a weird kind of a like, I love you to death, right? It's like okay, that's
stabs each other in the back.
Yeah, right. So that's
Biologically, we see something cute, we can't process it, so our instinct is to kill it.
yeah, right. I know. It's like,
Understand happiness.
yeah, we're like
Things can't
dogs.
be happy.
We're like dogs, right? I mean, if something weird happens in like a dog pack, they attack it, right? Even if it's like some poor other dog who's like having a stroke and they need help, it's like, do you help it? No, let's tear them apart. Come on, I don't understand what's going on, but it's like, let's kill it, right? It's like, yeah, it's like, I mean, it happens because, well, I've got like 6 dogs, right? So that's, and some of the dogs are getting older. So that's kind of what they do. They look at it, it's weird. And it's like, you're being weird. I might have to kill you. Right. I mean, it's like, how about help the dog? You know, like lay next to them, take care of them. But no, that's not what the pack does. We're all dogs, basically. That's all we are. We just think we're better than we are. But in reality, we're not really. Unfortunately, we try to be, right? And that's good enough for now. I mean, we try to be, but we're not, we don't get there. But anyway, so that's all well and good. Protons and neutrons and that sort of thing. And that does give us a lot of good stuff. However, in biology, we really want to focus our attention on the good stuff, right? So we want to focus our attention on electrons. And why electrons? The reason why we want to focus on electrons in biology and not so much on protons and neutrons, by the way, if you're focusing on protons and neutrons, you're probably in like a nuclear physics class or you're in a chemistry class, something like that. But we want to focus on electrons. Why? Because electrons, this is true right here. This is absolutely true. Electrons are the key to chemical behavior. The chemical behavior of atoms. Now think about this for a second. We have function, right? We have biological function that we're trying to put together. We got a task in front of us, build a biological organism. In order to do that, you have to establish certain tasks, right? You have to achieve certain functions. And some of those functions are going to require that sort of structure function sort of a thing, right? That is to say, you have to build some sort of specific structure to achieve your function, specifically designed. We just talked about that, right? Just not too long ago. So the question here then is, if I've got some particular function that I want, then a particular atom has to behave a certain way in order to give me that function. Who makes an atom behave in a particular way? The electrons. So I want to select a focus group, if you will, of atoms that have a very specific cherry-picked personality that will give me what I'm looking for. That will give me the personality, chemical personality that I need in order to achieve this task. Okay, it's like hiring. You're selecting that hot team. You want that red hot team, and you have to have certain personalities on that team that fit with each other. So you're looking for somebody very specific. Okay, that's what's happening here. When we're looking at the chemical behavior of atoms, it all comes from the electrons. It comes from their behavior, and understanding the behavior is what we want to do. Now, this is the reason why we use the Bohr model, because the Bohr model helps us to arrange, huge, right? It allows us to arrange these electrons in a schematic, the Bohr model, that helps us to understand better their specific chemical behavior. We can understand their chemical behavior, then we can start to very intentionally, very purposefully start to collect different personalities, put them together, and create specific molecules that we want to deploy. Okay. So that's the reason why we use the Bohr model, because we want to make this arrangement. We want to diagram these guys out. And typically speaking, part of this Bohr model brings us kind of this term called an orbit, right? So electrons basically will inhabit these orbits, very similar to like a planetary orbit, right? So they'll inhabit these orbits. And these orbits are basically, according to the normal, the real way, the spatial representation, that's going to be that cloud, right? Now, for the Bohr model, within that cloud are specific shape-like orbits within which the electrons reside. So imagine, if you will, that you're creating an electron cloud, let's say like the size of Denver, right? And within Denver, you have very definable, very well-shaped and organized neighborhoods, right? And different neighborhoods very much have a very different personality about them, right? I mean, we have the neighborhoods in and around here have a very different personality from the neighborhoods that are down south, from the ones that are out east, right? So the different neighborhoods have very distinct personalities in Denver. That's one of the interesting things about Denver. The neighborhoods are very distinct and have a very different personality to them. The same thing is true for the orbits. These are regions within the overall cloud within which these electrons reside, and they have this neighborhood type of personality to them. Now, here's the thing, and this is something you want to star and circle and box. hint, is typically by definition, in any given orbit, it can only have no more than 2 electrons. That's the max it can have. So when you're arranging these electrons in these sort of orbital neighborhoods within the overall structure of the atom, you can only have 2 electrons per orbital, okay, or per neighborhood. And so what I want to do, and this is probably, it's a little on the early side, but this is a good place to cut it because this is a good conversation to start off with. Unpacking this slide is going to take a few minutes. And not only that, but I want that orbital concept, the concept of an orbit within the overall cloud to kind of settle into your mind a little bit. And then what I want to do is I want to re-hit that one and reintroduce it and then unpack it a little bit and sort of bring this through a series of orbitals that we have here so we can kind of understand a little bit of the arrangement of the electrons and what information that gives us. Specifically, it's helpful for biology. Yes. Yep, this one. So now we're talking about electrons. So we're going to be leaving the neutrons and the protons behind, and we're going to be ever focusing on the electrons and how we can utilize these chemical behaviors that the electrons give these atoms to help us build our molecules. Think of colors of paints in the hands of an artist. An artist, like a Bob Ross, when they just know what shade of blue, like a shade of blue like that, right? They'll see a shade of blue, and then immediately they'll be thinking, okay, so what color combinations do I need to mix and in what ratios to get that exact color, right? So they need their 3 colors, and they know exactly just how much of phthalo blue to add to the white to wash it out to get exactly that color, that hue. They know exactly what to do to get some alternative color, like a darker shade of blue, right? Or any color in the spectrum for that matter. They know that, right? And so what they have is they have colors that can create behaviors, and they're basically taking the behaviors of their colors and they're mixing them together to create something new. And that's exactly what we're doing. We're using the personalities of the atoms, mixing them together to create something new that's going to help us build the structures we need to build our organism with. That makes sense? Okay, that's that. Next time we see each other, it'll be lab time on Friday.